Hello, my name is Ho Young-Kim, and I am an integrated student of the Gwangju Institute of Science and Technology in the Republic of Korea. The title of my today's presentation is Nematode-Inspired Cable Rod Method for Cable-Driven Redundant Manipulator. Cable-Driven Redundant Manipulator, known as CDRM, has been developed to enter a space that human cannot reach. Traditional CDRMs have unique cable routing methods that using three cables to control each universal zone. To achieve depth stage motion, this method requires as many motors and cables as the number of universal zones. However, this cable routing method has limitations in terms of thickness and load capacity. Hence, we propose a novel cable routing method for CDRM inspired by the muscle structure of nematodes. This cable routing method enhances the thickness and load capacity of CDRMs by mimicking the muscle structure of the nematode. To mimic the nematode muscle structure, we implement an alternately arranged moving spleen structure. Before introducing the proposed method, I will explain the basic concept. The basic concept of our proposed method can be explained through a simplified stiffness model based on the serial and parallel spring. The traditional cable routing method can be seen as a serial spring connection, while our proposed cable routing method can be seen as a parallel spring connection. For instance, when the cable winding number of the moving fluid is set to 3, the stiffness of our proposed method is approximately 7.5 times larger than that of the traditional method. Now, I will explain brief introduction of our Nematode-Inspired cable routing method. This is the schematic of the developed prototype. The proposed cable routing method is applied. In this cable routing method, single joint set 1 and 3 were constructed with a 45-degree offset, while single joint set 2 and 4 have a 0-degree offset. This configuration allows us to mimic the alternately arranged muscle structure within the actual CDRM. This is developed prototype that proposed cable routing method is applied. The table provides a list of the design parameters. The prototype is 3D printed using PLA plus material and strength steel wires with diameters of 0.27 mm were used for cable routing method. To verify the equation, we conducted kinematics and stiffness simulation. For the kinematics simulation, we employed the Jacobian method. The video demonstrates an example of the resulting circular trajectory. The stiffness simulation was conducted using the reference parameter at maximum and minimum stiffness configuration. The stiffness simulation results shows that the stiffness of the nematode-inspired cable routing method was 4 times larger than using moving fluid cable routing method alone. To evaluate the prototype, we conducted kinematics and stiffness experiments. For the kinematics experiment, we used cameras and object marker for tracking the position of the end itself. The video shows that trajectory tracking results. The RMSA error of the experiment was about 3 mm, approximately 3% in the radius direction. This error may have been caused by open-loop control error, especially due to the 3D printed body structure and the delay effect. In the stiffness experiment, the stiffness of CDRM was calculated by measuring the displacement caused by a given rate. The result shows that the single joint stiffness was 1.15 Newton per millimeter, while the multi-joint stiffness was 0.17 Newton per millimeter. The stiffness implication value was 6.74, was close to the estimated ratio. However, the stiffness of both experiments is smaller than that in other results. This is due to the 3D printed structure of the CDRM, as well as the use of cables with smaller stiffness for the experiment. For conclusion, we can say that the nematode-inspired cable routing method for CDRM can amplify stiffness while maintaining advantage of traditional CDRM. In future research, the accurate stiffness equation will be derived for the overall CDRM. After we will develop a prototype of the CDRM using steel cable and a steel body structure to improve the stiffness and payload capacity. In addition, we will apply feedback control to minimize the position error of the end effect. Thank you for listening.